Hey there, calculus fans. Continuing my series on proving the basic derivative rules. I just made one about proving the product rule and then proving the chain rule. The quotient rule is funny because I think typically in a course we don't prove it. We just use the other rules to prove it. But I'm going to prove this from first principles. I think I've rarely done that in my math career. So I'm glad to get to do that here and just get to show you another example of using the definition of the derivative. But what I always remembered it was, so you have the numerator and the denominator. So quotient rule means of some sort of fraction. So I always remembered it as denominator times the derivative of the numerator minus numerator times derivative of the denominator all over the denominator squared. Some students, since I started teaching, tell me they say low, and I'd never heard this before this, d high minus high d low. I think by d high they mean this. So low they mean denominator, all over the denominator squared. I always, as a student, just remembered it alphabetically. So if you know that D becomes a 4n, I just learned that a D goes here, and then the rest I could remember. Because I knew it was an n prime next to it, I knew there was a minus, and I knew the other one was the opposite, I knew the bottom was D squared. So I just remembered it alphabetically. That was when I was a student, that's how I remembered it. So it says how to put the things together. It says you're going to take the denominator and plop it in this spot. So I'm going to try to highlight as I go, since it's a lot of stuff. Highlight that. There's the denominator. What I tell students to do is to then leave some space and basically fill in everything that requires no brain cells. So now we're going to put in an n. That requires no brain cells. It's going to be 5x to the 2/3 plus 3x. Okay, great. And put a little dot. And then we're going to put fraction. And then we're going to do the denominator squared. So here's the denominator. It's this thing. Denominator squared. And by then you're probably exhausted. So then you go have dinner. And you come back. But the point I want to make is this separation of duties, of jobs, when you're doing this stuff. My 12-year-old would laugh that I said duties. Okay, so we need the derivative of the numerator and the derivative of the denominator. Derivative of the numerator, we're going to bring down the 2/3. So it's going to be, I'm going to write this here for those students that are struggling with their fractions. X to the negative 1/3. And altogether that's going to be 10/3. This is going to be x. Let me write the 10/3 as I intended to do. This is going to be 10/3. This is not pretty. I'm not claiming that every derivative is pretty. I'm just claiming we can take the derivative of anything and we're never scared of anything. And that's part of what's nice about derivatives. Okay, so we did that. Now we're going to do the derivative of the denominator. The derivative of the denominator is just 2x. Okay, at least something's kind of nice. And I tell students, if the goal is to find the derivative, you stop right then. Not because I'm against simplifying. I'm totally for simplifying. But I find most situations you're either trying to measure the slope somewhere, in which case you could already plug in your x, or you're trying to, and then you don't need to simplify. But if your goal is to solve, then it might be time to simplify. But even then, I might say, like, if I wanted to solve when it's equal to 0, I would first set it equal to 0 and then do some cleaning up from there. And I just picked a function that I thought looked sort of interesting. I mean, this one's got, as to the left as an asymptote, it comes up, it has a bump, it has this sharp point, and then it switches to a positive slope again, it has a bump. So these places, if I wanted to know where that high point was in this graph, which I can't seem to hit right on, my shaky old man hands. But if I want to know exactly where that was, it's about negative 0.47. But if I was going to try to solve, I would set this equal to 0, and then I'd have an algebra challenge of solving. An interesting thing happens as you move slightly this way. You can see the slope is becoming more and more negative. In fact, right there, the slope becomes infinite. It's going down. So we say the slope is undefined at 0, and you can see that in the tangent graph. We're not going to talk about that much in our business math class, but we definitely talk about it in a regular calculus series. And then we suddenly have this positive slope. Right at that point, the slope is 7.5. And then the slope is 4.15. And then we go to the peak. And the slope is 0 at about 0.8. That would be another solution you would get from this. You keep going. So there you go. If we wanted to analyze that graph on the left, the derivative itself is helpful. Okay, so now let's switch to this proof. So just like I did in the previous ones, I'm going to go directly, and I might finish this by proving it a couple different ways, but let's clear everything out. We know what our goal is. Our goal is to prove this. We're starting with a function that looks like f of x equals n of x over d of x. And we know where the derivative comes from. It comes from studying f of x plus h minus f of x over h. Watch my previous videos on that, but once again, we were just trying to define slope at a point. This took some discussion. Students were confused by this, but it always comes back to here, which is the slope between these 2 points. X, f of x plus h, in x, f of x. And we're just doing rise over run. Okay. Anyways, so now let's play the game yet again. Okay, so we're going to plug in an x plus h. So it's going to be n of x plus h over d of x plus h minus n of x over d of x, all divided by n. We're going to try to simplify this to a point where we identify the derivative. So just a reminder that if we ever can get to a point where it's n of x plus h minus n of x, I'm going to see how this proof goes. Like I said, I probably did this somewhere in my career, but I'm really not sure. It's going to be exciting if as we do this video on the fly. So we know that I have a feeling we can do it. We know that this is going to approach n prime of x. We know that this is going to approach d prime of x. That's going to appear in my method, but it's a question of where all the other mess comes from. Now, I have a certain rule I tell students about fractions inside of fractions. First, I hate them. I don't want to have fractions inside of fractions. So if somebody gives me this, I don't do any sort of figuring out the flipping and all the stuff that students do. I just clear the denominator, meaning I multiply top and bottom by 15. You might say, where am I getting the 15? Well, it's me trying to get rid of the 3 and the 5. That'll get rid of the fractions within fractions and clean it up. So I'm going to follow my same policy here for myself. I was going to do that when I was first thinking about this. I said, I'm like, no, let's follow what I tell students to do, which is I'm going to do d of x plus h. I'm going to multiply by this because that's going to get rid of all the fractions in the numerator. But I have to multiply top and bottom. So the same idea as some of the other proofs. We're just trying to rewrite it in a form we can recognize. When you multiply this times this, the dx plus h will cancel. When you multiply this times this, the dx will cancel. Okay, so we have n x plus h times dx minus nx times dx plus h. And on the bottom, we have h times dx plus h times dx. And that already looks a little promising to me because it looks like as h goes to 0, we're going to get a d squared on the bottom, which is part of the formula. Well, that's kind of fun. Okay, So at this point, I feel like I want to fall back on the strategy we used for the product rule. Let me think about this. Again, I can't remember if I've ever done this before, so we're going to do it on the fly. I'm going to put a minus, and I would like an n prime to appear here. So I think what I'm going to do is I'm going to write nx and dx. But I can't just randomly put something in the middle. Maybe what I should have done, what I meant to do, was leave this in green. This is the bad part about not preparing. I don't think about the visual optics of how it's going to go. Then there's going to be a plus n of x, d of x. Oops, I didn't grab the fat pen. See all these mistakes I'm making. I think in math sometimes we make the mistake of thinking everything has to be polished. It doesn't have to be. A proof isn't like that. I mean, it's good to make it clear, but I would like you to see how we think through this and it's not some sort of magic. Okay, so what I did is I added this thing in the middle in hopes that I could rearrange. It looks like I forgot to copy this. Okay, now what can we do? We can factor a d of x out of the first two. Again, I'm using the same strategy we used for the product rule. So this is confusing. Check that out. Yay. Plus, we can take an n of x out of the other one. Ooh, this is starting to look like my rule. But there's a couple little things that are bugging me. And then we're dividing all this by this h and this other stuff. Now, what I really want to do the moment I see this, and I'll do it in two steps, is I want to separate my fractions just like I did when we did this with the product rule, but I'll write it here. D of x times h, d of x plus h, d of x times h. Whew! That's a lot of stuff. So I separated these two things. I just broke it into these two fractions and cleaned it up a little bit. Now, what I see, what I mentioned at the beginning, is we should be looking for this. That is approaching n prime. There is a little problem here. That's not quite d prime because these two things are in the wrong spot. So we're going to flip them. But you can't just flip something. I mean, if you're doing, 5 minus 7, you're going to get negative 2. And if you flip and do 7 minus 5, you're going to get 2. So you can't just flip those locations. But wait, you can. It's just going to change the sign. Somebody made this observation. Well, okay, we can handle that. So this is going to approach d of x. This whole thing is going to approach n prime of x. I'm being a little less than formal here. But again, I'm not worrying about a formal proof. I'm saying this is going to get closer and closer to n prime. And then over here, instead of a plus, I'm going to write a minus. And then I'm going to flip those two. So then I'm going to have n of x. And that's going to be approaching d prime. And that's where the minus is coming from. Now, I already started to do it, but as h goes to 0, this is just going to be, the bottom is going to become d of x squared. Now, you could leave those separately. So I guess that gives us another formula. dn prime over d squared minus nd prime over d squared. That's also correct. In fact, you could even cancel those d's and write it as n prime over d squared minus nd prime. It's not to the first, over d squared. But at some point, somebody's like, that just doesn't, none of those look that pretty. And so some textbook decided to write it this way. And then we continued to do it. d squared. So there we go. There's our quotient rule. Okay. One last thing I was going to say here is what a lot of students tell me they like to do, which is fine. I think it is nice to know the quotient rule. But some students tell me when they're given a fraction, they're given x plus 1 over x squared plus 3. They like to rewrite it as x plus 1 times x squared plus 3 to the negative 1. And then they can do it like a product rule, but they also need to know the chain rule to do that, meaning they call this the first, they call this the second, and they use the chain rule. And that is perfectly fine. I do think in this situation I would rather use the quotient rule because I just think it's more direct. But I'm fine with that. Okay, but that does give you a secondary proof approach, which is to say, okay, I already know the product rule, and I already know the chain rule. So I could write it this way, and then apply the rules I already know. So let's do that approach too, since I'm doing a proof. Let's call this the first. Let's call this the second. So we're going to do first, so the derivative of this thing, try and take the derivative, is going to be first, that's the first, times the derivative of the second. Now that's going to require the chain rule. So we do negative d of x. So I brought down the negative 1. I made it a negative 2. This is all times. I don't know how to write this. Times the derivative of the inside, d prime of x. So that's the first part. This was the derivative of s. And then you're going to write plus, and then we're going to do the derivative of the first, which is n prime of x, times the second, which is d of x to the negative 1. So that's also a correct formula, but nobody writes it that way. They would write n of x. They'd rewrite all this. There'd be a negative from there. There'd be a d prime of x from there, all over d of x squared. That would be this first term. And the second term would be n prime of x over d of x. You might say, is that the same rule? It's one of the versions we talked about. So typically what somebody was like, well, I kind of like to put the minus in between. So rearranging and making it look a little prettier. You get this. And then if you get a common denominator, you're going to have a d of x here, and this is going to be a d of x squared. And if you put it together, there's yet again our rule. Denominator times derivative of the numerator minus numerator to the denominator over the denominator squared. Okay, hope you have found these interesting. Everything goes back to this definition. We're just using it in different settings and building up a collection of rules so that we can do this. And what's cool is you can give me almost any complicated function and we can compute the derivative. Sometimes the derivative is kind of ugly, but we still can get it. And then we can put it into a solver. Solve when the derivative is 0. And that some people go, well, can't you just graph that? The bigger value is, what if you're studying a collection of functions, like you have a parameter in there and you're trying to fit it to some data. At that point, you can't graph it because you don't know what the parameter is. But you can still do this analysis, and then you can use the analysis to figure out what parameter you want. That is a very common situation. So the idea that we can analyze something and get it precisely without a graphing device is really important. So hope you find that